Unit 3, Quantities and Chemical Reactions. Section 6.3, the mole, a unit of counting. The mole is a unit of counting in chemistry, and you're familiar with other units of counting. For example, 1 dozen equals 12 of something. For example, 12 golf balls. A 6-pack is 6 cans of pop. 1 ream is 500 sheets of paper. And 1 hour is 60 minutes. The definition of a mole is a unit of amount, the amount of substance containing 6.02 times 10 to the power of 23 entities. And the symbol for the unit of the mole is MOL. Avogadro's constant. Avogadro's constant, symbol N subscript A, is the number of entities in 1 mole of a substance. 1 mole of a substance has 6.02 times 10 to the power of 23 entities. Like other SI base units, such as the meter and the kilogram, the mole is defined against a known standard. The standard chosen to define the mole is the number of atoms in exactly 12 grams of carbon. Here we have a diagram that shows equal amounts of carbon atoms and sulfur atoms, 1 mole of each. Both samples contain 6.02 times 10 to the power of 23 atoms. The sulfur sample has a larger volume and a greater mass because sulfur atoms are larger and heavier than carbon atoms. Similarly, a dozen tennis balls occupy a larger volume than a dozen golf balls. Please read over section 6.3 and answer any questions to familiarize yourself with the concept of the counting unit, the mole. (6.4) Molar mass. Molar mass is given the symbol capital M, and it's the mass of 1 mole of a substance, and the unit symbol is grams per mole. You can look on a periodic table to find a couple of important pieces of information. The first is the atomic number. Carbon has atomic number of 6, but also a secondary quantity which is called the molar mass. The molar mass of carbon is 12.01 grams per mole of carbon. So the atomic mass of carbon, 12.01 atomic mass units, has the same numerical value as 1 mass of mole of carbon, 12.01 grams. We can write the molar mass as a capital M with a subscript for the symbol of the element, so the molar mass of carbon can be written as 12.01 grams per mole. We can use a periodic table to find the molar mass of other substances. The molar mass of oxygen is 16. Let me just reference my periodic table. .00 grams per mole. The molar mass of potassium is 39.09 grams per mole. And the molar mass of neon is 20.18 grams per mole. Let's find the molar mass of compounds. To find the molar mass of compounds, we're going to add up the molar mass of each of the elements that are present. So the molar mass of hydrogen phosphate is equal to 3 times the molar mass of hydrogen plus the molar mass of phosphorus plus 4 times the molar mass of oxygen. Hydrogen has a molar mass of 1.01 grams per mole. Phosphorus has a molar mass of 30.97 grams per mole. And oxygen has a molar mass of 16.00 grams per mole. You can find the total by adding up all of these quantities. And the molar mass of hydrogen phosphate is 98.00 grams per mole. Let's find the molar mass of the compound sodium chloride. That's equal to the molar mass of sodium plus the molar mass of chlorine. Using a periodic table, we can see that the molar mass of sodium is 22.99 grams per mole, and the molar mass of chlorine is 35.45 grams per mole. Adding these together, the molar mass of sodium chloride is 58.44 grams per mole. So 1 mole of sodium chloride would have a mass of 58.44 grams. Let's find the molar mass of calcium chloride dihydride. So it's the molar mass of calcium plus 2 times the molar mass of chlorine plus 2 times the mass of H2O and remember that H2O has 2 hydrogen and 1 oxygen. So we can use our periodic table. Calcium has a molar mass of 4.08 grams per mole, and chlorine 35.45 grams per mole. Hydrogen 1.01 grams per mole, and oxygen 16.00 grams per mole. If you punch this in, the molar mass of calcium chloride dihydride is 147.02 grams per mole. So again, 1 mole of calcium chloride dihydride would weigh 147.02 grams. Or we can say 6.02 times 10 to the power of 23 particles of calcium chloride dihydride would weigh 147.02 grams. Now we can do calculations involving molar mass. The number of moles is equal to mass divided by molar mass, where n equals the number of moles, lowercase m is the mass in grams, and capital M is the molar mass in grams per mole. According to the manufacturer, a typical can of cola contains 40.0 grams of sucrose, C12H12O11. Calculate the amount of sucrose in 40.0 grams. So what we're looking for is the number of moles of sucrose, or the number of moles of sucrose in 40 grams. So we can write the equation number of moles equals mass divided by molar mass in an equation triangle where this horizontal line means divided by and this vertical line means multiplied by. So the number of moles, we're going to find it. Number of moles is equal to mass divided by molar mass. We have a mass of 40.0 grams. What we need to find is the molar mass of sucrose. So that's equal to 12 times the molar mass of carbon plus 22 times the molar mass of hydrogen plus 11 times the molar mass of oxygen. The molar mass of carbon is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. And oxygen is 16.00 grams per mole. The total molar mass is 342.34 grams per mole. So I want to know how many moles that is. So the number of moles equals mass over molar mass. In 40 grams, if the molar mass is 342.34, I can punch this into the equation, and if we solve, we end up with 0.0117 moles of sucrose in 40 grams. Similarly, we can do a sample problem where we calculate the mass from an amount. A liter of human blood contains 4.0 millimoles of glucose, C6H12O6. Calculate the mass of this amount of glucose. With the equation triangle, we can find the mass by multiplying the number of moles times the molar mass. The molar mass of glucose is 6 times the molar mass of carbon plus 12 times the molar mass of hydrogen and 6 times the molar mass of oxygen. So that's 6 times 12.01 grams per mole plus 12 times 1.01 grams per mole plus 6 times 16.00 grams per mole. And the molar mass of glucose is 180.18 grams per mole. So let's find the mass of 4.0 millimoles times the molar mass, 180.18 grams per mole. Now, in this example, they gave us the number of moles in millimoles. We have to convert that into moles. The prefix milli means 10 to the power of -3. So that's 4 times 10 to the power of -3 moles times 180.18 grams per mole. If we punch that into the calculator, we end up with a mass of 0.72 grams of glucose. Please try any homework problems corresponding to this section. 6.5, mass and number of entities. The diagram shows a sample of water in a graduated cylinder. 1 mole of water has a mass of 18 grams. Since water has a density of 1 gram per milliliter, then 18 milliliters, 1 mole of water, contains 6.02302 times 10 to the power of 23 water molecules. 1 mole of water has 6.02 times 10 to the power of 23 entities. 6.02 times 10 to the power of 23, this is Avogadro's number. This is the number of entities in 1 mole. Now we can find the number of entities in a given number of moles by calculating the number of moles times Avogadro's number. Remember that Avogadro's number is 6.02 times 10 to the power of 23 entities per mole. Sample problem number 1, calculating the number of atoms in a sample. Calculate the number of atoms in a 1 kilogram bar of gold. In this question, what we want to find is the number of entities of gold in a 1 kilogram or 1.00 times 10 to the power of 3 gram sample of gold. And we know that Avogadro's number is 6.02 times 10 to the power of 23 grams per mole. So in order to do so, I need to find the number of moles in a 1 kilogram bar of gold. So the number of moles is equal to the mass, and we know the mass is 1 times 10 to the power of 3 grams. So first thing I need to find is M, the molar mass of gold. If you look on a periodic table, the molar mass of gold is 196.97 grams per mole. So the number of moles is equal to mass over molar mass. That's 1.00 times 10 to the power of 3 kilograms divided by the molar mass of 196.97 grams per mole. If we punch this into our calculator, we end up with 5.076 moles. Now to find the number of entities, it's equal to the number of moles times Avogadro's number. So the number of entities of gold is going to be equal to 5.076 moles times Avogadro's number, 6.02 times 10 to the power of 23 entities per mole. If we punch this into our calculator, we end up with 3.06 times 10 to the power of 24 atoms of gold, or entities of gold. Let's see if we can calculate the number of molecules in a sample. Calculate the number of molecules in a sample. Ammonia is a pungent gas released from smelling salts. Calculate the number of molecules in a 4 milligram sample of ammonia. So in this question, we are given the mass of ammonia, 4.00 milligrams, which is 4.00 times 10 to the power of negative 3 grams. And we want to find the number of entities of ammonia. So the number of entities of ammonia is equal to the number of moles of ammonia times Avogadro's number. To find the number of moles, we're going to use mass over molar mass. So we need the molar mass of ammonia. And the molar mass of ammonia is the molar mass of nitrogen plus 3 times the molar mass of hydrogen. That is 14.01 grams for nitrogen plus 1.01 grams per mole times hydrogen. So the molar mass of ammonia is 17.04 grams per mole. So we can find the number of moles of ammonia as the mass 4.00 times 10 to the power of negative 13 grams divided by a molar mass of 17.04 grams per mole. We can find the number of moles by dividing these two, and we end up with 2.35 times 10 to the power of negative 4 moles of ammonia. So we're going to use this information to find the number of entities of ammonia. It's equal to the number of moles of ammonia, 2.35 times 10 to the power of negative 4 moles, times Avogadro's number, 6.02 times 10 to the power of 23 entities per mole. If we punch this in, we end up with 1.41 times 10 to the power of 20 molecules of ammonia. In 4 milligrams of ammonia. Next, let's calculate the number of atoms. Benzaldehyde, C7H6O, is a compound used to give prepared foods an almond flavor. Find the number of carbon, hydrogen, and oxygen atoms in a 2.65 gram sample of benzaldehyde. So what we're going to do in this example, write down what's given. We have a mass of 26.5 grams. And first thing we're going to do is find the molar mass of C7H6O, which is 7 times the molar mass of carbon, plus 6 times the molar mass of hydrogen, plus the molar mass of oxygen. That's 7 times 12.01 grams per mole from carbon, plus 6 times 1.01 grams per mole for hydrogen, plus 16.00 grams per mole for oxygen, and the molar mass of benzaldehyde is 106.13 grams per mole. So how many moles does this represent? How many moles of benzaldehyde are present in 26.5 grams of a substance? Well, the number of moles is equal to mass divided by molar mass. So the mass is 26.5 grams and the molar mass is 106.13 grams per mole. This gives us a molar mass of 0.250 moles of benzaldehyde. Now, we can find the number of entities of benzaldehyde by by finding the number of moles of benzaldehyde times Avogadro's number. So the number of moles that we've determined was 0.250 moles. And multiply this by Avogadro's number, which is 6.02 times 10 to the power of 23 entities per mole. This gives us 1.503 times 10 to the power of 23 molecules of C7H6O benzaldehyde. Now, each molecule contains 7 carbon atoms. So to find the number of carbon atoms, we're going to multiply 7 times the number of molecules which is 7 times 1.503 times 10 to the power of 23. And we end up getting 1.05 times 10 to the power of 24 atoms of carbon. Now, there are 6 hydrogen atoms per molecule. So if we know the number of molecules, we can multiply that by 6. The number of entities is the same as the number of molecules. I just want to take this time to show us what we're doing here in a little bit more detail. There's 6 atoms per molecule. And there are 1.503 molecules in the sample. So when we compute this, we get 9.02 times 10 to the power of 23 atoms of hydrogen in the sample. We'll do the same thing for the number of oxygens. There's 1 oxygen atom per molecule. So that's 1 times the number of molecules, which is 1.503 times 10 to the power of 23. So there are 1.503 times 10 to the power of 23 atoms of oxygen in the sample. In the next example, we're going to convert the number of entities to moles. A sample of carbon dioxide contains 1.42 times 10 to the power of 25 oxygen atoms. How many moles of CO2 molecules are there present? So, calculate the number of moles of oxygen atoms. We know Avogadro's number tells us that there are 6.02 times 10 to the power of 23 atoms per mole. So to find the number of moles, of oxygen, we're going to use the equation. Number of entities is equal to moles times Avogadro's number. So the number of moles is going to be equal to the number of entities divided by Avogadro's number. So the number of entities divided by Avogadro's number is 1.42 times 10 to the power of 25 oxygen atoms per mole, or atoms rather, divided by 6.02 times 10 to the power of 23 atoms per mole. If we punch this in, we end up with 23.6 moles of oxygen. Now, to determine the number of moles of CO2 molecules, this is important. Each mole of CO2 contains 2 oxygen atoms. So to find the number of moles of CO2, we have to take the number of moles of oxygen and divide it by 2. Because each molecule contains 2 oxygens. And if there's 23.6 moles of oxygen, divided by 2, that means that there are 11.8 moles of CO2, because each CO2 molecule contains 2 times the amount of oxygen. Therefore, there are approximately 11.8 moles of CO2 in the sample. Please take some time to try the practice problems outlined below. Don't forget to use your solutions manual to help you through these questions, especially when they get difficult. (6.6) Percentage composition. The law of definite proportions. The elements in a compound are always present in the same proportion by mass. Percentage composition is the percentage by mass of each element in a compound. You can find the percentage composition of an element using this equation. The percent of an element is equal to the mass of the element divided by the mass of a sample times 100%. Let's try a sample problem. Calculating composition from lab data. A 500 milligram tablet of aspirin, C9H8O4, contains 300 milligrams of carbon and 8.08 milligrams of hydrogen. The remaining mass is oxygen. Determine the percentage composition of aspirin. Step 1. Use the percent element formula above to calculate the percentage composition of each element for which you know the mass. Let's start with the percent composition of carbon, which is equal to the mass of carbon divided by the mass of the sample times 100%. We know that there is 300 milligrams of carbon. That's 300 times 10 to the power of negative 3 grams of carbon divided by the total mass of the sample, 500 milligrams, which is 500 times 10 to the power of negative 3 grams times 100%. If we punch this into our calculator, we get 60.00% carbon. We can do the same to find the percent composition of hydrogen, which is equal to the mass of hydrogen divided by the mass of the sample times 100%. The mass of hydrogen is 8.08 grams or milligrams. We can also write that in grams as 8.08 times 10 to the power of negative 3 grams divided by 500 times 10 to the power of negative 3 grams times 100%. And we end up with 1.62% hydrogen. In step 2, we determine the percent of the element for which we do not know the mass by subtracting the sum of the percentages of the other elements from 100%. The remaining mass of aspirin in the tablet is oxygen. So the percentage of oxygen we're going to subtract from 100% the percentage of carbon and the percentage of hydrogen. And we end up with 38.8% oxygen. Therefore, the percentage composition of aspirin is 60% carbon, 1.62% hydrogen, and 38.38% oxygen. Let's try an example where we calculate composition from the chemical formula. Determine the percentage composition of calcium hydroxide, which has the chemical formula CaOH2. Step 1. Calculate the molecular mass of the compound. The molecular mass of calcium hydroxide is equal to the molecular mass of calcium plus, let me just correct this, 2 times the molecular mass of oxygen plus 2 times the molecular mass of hydrogen. The molecular mass of oxygen we can get from a periodic table. Let me call mine up. So calcium has a molecular mass of 40.08 plus 2 times the molecular mass of oxygen. And remember, these are grams per mole. and the molecular mass of hydrogen is 1.01 grams per mole. So the molecular mass of calcium hydroxide is 74.10 atomic mass units, or grams per mole. Step 2. Calculate the percentage of each element by dividing the total mass of the element by the molecular mass and multiplying by 100%. So the percentage of calcium is equal to the mass of calcium divided by the total mass, which is 40.08 grams per mole, divided by 74.10 grams per mole. Multiply that by 100%, and we get 54.09%. The percent of oxygen is equal to 2 times the molecular mass of oxygen, because in the chemical formula they tell us that there are 2 elements of oxygen, divided by the molecular mass of the compound. Multiply this by 100%, and we end up with 43.18% oxygen. And the percent of hydrogen, since there are 2 hydrogen, 2 times the mass of hydrogen divided by the total mass times 100%, we end up with 2.73% hydrogen. If you add up all of the percentages, we should be equal to 100%. And we just verified that all of these percentages add up to 100%. Therefore, the percentage composition of calcium hydroxide is 54.09% calcium, 43.18% oxygen, and 2.73% hydrogen. Please try any practice problems assigned, and don't forget to read the section as well.